Hi everyone, I'm Nadiia Chepurko, and today I will be talking about sample optimal low-rank approximation for PSD matrices. This is a joint work with Ainesh, Bakshi and David Woodruff. This talk is divided into three main parts. I will start with a primer on low-rank approximation. Next, I will describe our results, comparison to prior work, and some applications of our results. Then, Ainesh will take over and describe some new techniques we introduced in this work. Okay, let's start with a primer on low-rank approximation. Here, we are given as input n by d matrix A and an integer k. And the goal is to factor A into n by k matrix U and k by n matrix V such that the product of U and V is close to A. Note, this decomposition forces the product U times V to have rank at most k. We can write this more formally as the following optimization problem. We want to find matrices U and V of rank at most k such that their product is close to A in squared Frobenius norm. Recall, the squared Frobenius norm is just the sum of squares of the entries. Let us briefly consider the motivation behind studying low-rank approximation. It is an important algorithmic primitive in many data science and machine learning applications to compress massive datasets and reduce the number of effective parameters. Such a factorization is also often used to detect structure in data, unsupervised clustering, statistical modeling, distribution learning, and so on. To understand the structure of a low-rank approximation, we begin with a singular value decomposition. Given a symmetric matrix A, the singular value decomposition is represented as a product of three matrices. Q, a matrix with orthonormal columns, sigma, a diagonal matrix with the singular values along the diagonal, and Q transpose. We can then obtain a low-rank matrix from the singular value decomposition by truncating all but the top k singular values in sigma. Observe, the resulting matrix is rank k, and in 1936, Eckert and Young show U equals Q sigma k and V equals Q transpose is the optimal solution to the low-rank approximation problem. Now that we have characterized the optimal solution, let us consider the computational complexity of computing it. There are three main approaches to compute the truncated SVD. We can compute it exactly using Cholesky factorization, but this requires n to the omega time, where omega is a matrix multiplication constant. We can also use iterative methods, which either depend on singular value gaps or an approximate proxy to them. And finally, we can use randomized algorithms, which will be the focus of this talk. A long line of work on randomized algorithms culminated in 2013 paper by Clarkson and Woodruff that showed how to compute a rank K matrix B such that Frobenius cost of B is at most 1 plus epsilon times the cost of the truncated SVD. Recall, the cost of the truncated SVD is optimal. Further, the running time of this algorithm depends on the number of non-zero entries in A. In other words, the running time is linear in the size of the input. It is also not too hard to see that reading the entire input is necessary. Consider a matrix with all ones and one really large entry placed randomly. Observe, this matrix has rank 2, and thus the optimal rank 2 approximation has 0 squared Frobenius cost. This implies a rank 2 approximation to matrix must detect the large entry. Otherwise, the cost can be arbitrarily large, while the optimal cost is 0. Since the large entry was randomly placed, the algorithm must read the entire matrix. In this work, we consider low-rank approximation for structured instances, such as when the input matrix is positive semi-definite. Recall, PSD matrices have the following equivalent characterizations. All of its eigenvalues are non-negative, or it can be factored into matrices Q, Q transpose for some matrix Q, or all quadratic forms are non-negative, meaning X transpose AX is non-negative for all vectors X. A motivating example to keep in mind is computing a low-rank approximation for a covariance matrix. Consider the case where you have a large data matrix with n points in d dimensions, and let this matrix be denoted by D. The empirical covariance matrix is then given by D transpose D. Many tasks in data analysis require computing the top K subspace of the covariance matrix. Further, storing all entries of D transpose D might require too much space, and instead we would like to store a compressed representation of it. The central question in this work is whether computing a low-rank approximation requires reading the entire input when the input is promised to be in positive semi-definite form. This question was first addressed by Moscow and Woodruff in 2017, and they showed that reading the entire input is not necessary. In particular, there is randomized algorithm that reads only linear in n entries to compute a low-rank approximation, which can be much smaller than the sparsity of the matrix. However, this algorithm incurs a polynomial dependence on the target rank and desired accuracy for both the query complexity and the running time. Their algorithm roughly works as follows. Given a PSD matrix, it queries a linear in n number of entries in this matrix as follows. And only looking at these entries, it obtains a low-rank approximation to A. Further, Moscow and Woodruff also showed a lower bound on the number of queries required for a PSD matrix. And this says if any algorithm queries less than linear in A, K, and 1 over epsilon entries in A, then it is information theoretically impossible to output a low-rank approximation. To summarize these results, the picture looks as follows. Here we have the query complexity along the x-axis, and above this threshold of nk over epsilon to the 2.5, we have efficient algorithms. And below this threshold of nk over epsilon, the problem is impossible. The question we focus on is, what is the optimal dependence on epsilon? One foreseeable obstacle to determine the optimum dependence is that a quadratic dependence on 1 over epsilon seems inherent in the proof strategy. Typically, we use concentration of measure style arguments which incur this quadratic dependence. Our main result is to show that the optimum sample complexity is linear in the dimension of the input n, the target run k, and the target accuracy epsilon. And the quadratic dependence can be avoided. Further, the running time is also linear in all 3 parameters if the matrix multiplication constant is 2. The updated picture then looks as follows. We again have query complexity on the x-axis and the running time on the y-axis. Our result implies that we get a nearly linear time algorithm at this threshold of nk over epsilon. Below this threshold, the problem is information theoretically impossible. We therefore obtain a sharp phase transition with no computational versus statistical gap. Consider the problem where, in addition to the input A being a PSD matrix, we are required to output a low-rank approximation matrix B that is itself positive semi-definite, as you can see in the box. We show that we can extend our techniques to obtain an algorithm for this problem, again with a linear dependence on the dimension n, the target rank k, and the accuracy parameter epsilon. Such a constraint shows up in several applications, such as correlation matrix recovery, where the goal is to recover a low-rank correlation matrix, which is PSD. Prior work on this problem by Masco and Woodruff gets polynomially worse dependence on k and epsilon. Next, consider the problem where the input, instead of being PSD, is promised a negative type metric. Here, we consider a point set x1 to xn, and the corresponding distance matrix is of negative type if the ijth entry of A is a squared Euclidean distance b over w, xi, and xj. In prior work, Bakshi and Woodruff showed that we can obtain a bicriteria algorithm for this problem, where we output a rank k plus 4 matrix that has cost comparable to the best rank k approximation. And central conceptual question left open was whether this bicriteria guarantee is necessary. While it may seem like this problem is completely unrelated, we show that our techniques enable us to obtain a pure low-rank approximation for negative type matrices with no bicriteria dependence and optimal sample complexity. We also obtain faster algorithms for ridge regression, which can be found in this paper. I will hand over to Ainesh, and he will describe some of the new techniques that we introduce in this work.
Okay, thank you, Nadiia. Let us begin with some intuition as to why we can get away without reading the entire matrix. So consider the hot example from before, where we have a matrix where all but 2 entries are 1, and there is one entry selected uniformly at random and set to be really large. To make the matrix symmetric, we can set the corresponding entry in the lower half of the matrix to also be really large. So now this matrix is symmetric and has real eigenvalues. However, it's not too hard to see that this matrix is actually not PSD. While there are multiple ways to see this, we will focus on the following property of PSD matrices. The diagonal of a PSD matrix upper bounds all off-diagonal entries. To see a quick sketch of this proof, recall that any PSD matrix A can be written as a product of X transpose X for some matrices X. Okay, so this means that the ijth entry of A can be represented as the inner product of the ith and jth columns in X. Now, by Cauchy-Schwarz inequality, the square of any off-diagonal entry is given by the squared inner product of xi times xj, and this is less than the ith and jth squared diagonal entry given by the two terms here. So as we can see, this shows that the diagonal entries are upper bounds on the off-diagonal entries, which rule out such instances. Okay, with that intuition in mind, let's consider a high-level geometric overview of our algorithm. So our algorithm roughly has 2 steps. First, we find a coarse low-rank approximation where we modify the target rank and set it to be significantly larger than our original target rank, which was k. The coarseness here refers to the accuracy of the low-rank approximation that we compute. Note that our target accuracy is a 1 plus epsilon approximation, but in the first step, we suffice for a constant approximation. Well, then given this coarse approximation, we find a rank k low-rank approximation in the subspace that we recovered from the first step. So a caricature to keep in mind is as follows. So let the green sphere here denote the subspace spanned by the columns of the input matrix A. So this is a subspace that spans R to the n. We then compute a k over epsilon dimensional subspace of the column space of A and we denote this by the blue sphere over here. We show that this subspace contains a coarse low-rank approximation for A. Given this subspace, we then compute a k-dimensional subspace denoted by the yellow sphere here, and show that projecting A onto this subspace gives us our desired matrix B, which satisfies this guarantee here. So that's the high-level approach of our algorithm. Okay, from a linear algebra perspective, our algorithm proceeds as follows. We start off with an n by n PSD matrix A and sample square root nk over epsilon columns of A to obtain a matrix C. The matrix C has the property that the subspace spanned by its columns is closed to the subspace spanned by the columns of A. We then sample square root nk over epsilon rows of C to obtain a matrix R such that the row span of R satisfies the same property as before. That is, it is close to the row span of C. Since R has only nk over epsilon entries, we can afford to compute R exactly. We can afford to query R exactly and compute the truncated SVD for the desired rank k over epsilon. Okay, so now we have access to this matrix, which we computed. But now, this matrix does not match either dimension with A, and it is unclear how to go from this low rank approximation for R to a good low rank approximation for A. Given the time constraints, I will not be able to go into all the details of this part of the algorithm, and instead, I will distill part of this algorithm as a standalone problem and show how to solve it. The entire reduction, of course, appears in the overview section of our paper. Okay, so let's focus on the problem I mentioned before. But before I define this problem, let us begin by recalling the following easier problem, which is called multi-response regression. Here, we are given an n by m matrix Y and a d by m matrix Z. And we consider the following optimization problem. We want to find the minimum x such that y minus x times z is small in a Frobenius norm. Note, this problem is a straightforward generalization of the least squares regression problem to the matrix setting. This problem is really well studied, and in fact, it admits a closed form solution using normal equations. Okay, now we are ready to define a variant of this problem, which we refer to as spectral regression. Here, we're again given access to matrices Y and Z, and we want to find a matrix X that now minimizes the spectral norm difference between these two quantities. Compared to the previous problem, we have simply replaced the Frobenius norm here by the spectral norm. But now this problem is quite different from the previous one in that the geometry of this problem is different, and we no longer have access to orthogonal projections in this norm space given by the spectral norm. To the best of our knowledge, this problem has not been considered before in the context of low-rank approximation, and in fact does not have much prior work. While we can show that we can solve the spectral regression problem in full generality, for our application to PSD low-rank approximation, we will consider the following special case of this problem. So we are again given matrices Y and Z, but now we are also promised that Z has orthonormal rows. The key algorithmic question that we are now interested in is, can we approximately solve spectral regression in sublinear queries to the matrix Y? And we end up showing that we actually can solve this problem. In particular, we obtain a 1 plus epsilon approximate solution by querying only n d over epsilon entries in Y, Recall Y was an n by m matrix, and D can be much smaller than m. We also characterize the approximate optima of this problem. At a high level, our algorithm proceeds as follows. We sample D over epsilon columns of Y and Z. The picture to keep in mind for this is as follows. So we have these matrices Y and Z, and we sample columns of Y and the same set of columns in Z. And we obtain these smaller matrices, which we denote by Y times S and Z times S. Okay. We then solve spectral regression on this considerably smaller instance, and we in fact obtain exact algorithms to solve this sketch problem. Okay, so let us consider how to sample these columns. Since we want to minimize the number of queries to Y, a natural way to sample these columns would be to uniformly sample them. However, if we do the analysis using uniform sampling, we can show that we in fact incur a condition number dependence in the number of columns that we require to sample. And this gives us suboptimal query algorithms. Okay, instead, we will sample the columns of Y proportional to the leverage scores of Z. Since we assumed that Z had orthonormal rows to begin with, the leverage scores of Z are simply the column norms of Z, and these can be computed efficiently. Further, observe our sampling process is completely agnostic to the entries in Y. We can also show that the sketch that we compute based on leverage score sampling approximately preserves the matrix product Y times Z transpose. We know that this analysis is really new since all prior constructions preserving matrix product in spectral norm were either oblivious sketches or relied on reading the entries in Y. And we do not do either of these here. Okay, next, in order to analyze the cost after the sketch, we appeal to what are known as spectral norm decay results. So here we are given an arbitrary matrix M, which is n by n, and we sample q columns of this matrix uniformly at random. After sampling the columns, we denote the resulting matrix by M sub q. We are interested in the question of how the spectral norm of M sub q relates to the spectral norm of M. To understand this question, we appeal to a beautiful theorem of Rudolphson and Verschonen from 2004 that relates these quantities as follows. So on the left-hand side here, we have the expected spectral norm of this random matrix M sub q, where we have sampled q columns of M. And this is upper bounded by root q over n times the spectral norm of the original matrix, plus this additive term, which depends on the max row norm of M. So this theorem states that the spectral norm roughly decays proportional to square root q over n for dense matrices M. However, this result does not suffice for our application in a black box way, since we are not sampling columns uniformly at random, as we discussed on the previous slide. Okay, so we extend the results of Rudolphson and Verschonen to non-uniform sampling. Here, we sample q columns of M non-uniformly, given some regularity conditions that I will not get into here, and show that the expected spectral norm again decays at the same rate as uniform sampling. And of course, you again incur this additive term. Okay, so let's see how we can use this new result in our algorithm. So the outline of our algorithm now is as follows. We start off by sampling d over epsilon columns of Y and z according to the leverage scores of z, which we can compute efficiently. We then use the non-uniform spectral decay guarantee from the previous slide and show that the sketched problem actually preserves the cost of the spectral regression. We then solve the sketched spectral regression problem, which is a much smaller instance, and we show how to solve this exactly. In fact, we give a closed form solution for it. Okay, that completes the technical overview of our work. Before concluding, I would quickly like to highlight this new model for robust low-rank approximation that we introduce in this work. We consider the following corruption model. Let A be an arbitrary PSD matrix and E be a corruption matrix such that the Frobenius norm of E is small compared to the Frobenius norm of A. So given access to A plus E, can we compute a low-rank approximation to the original matrix A? So this additive corruption model is designed to capture real-world data, which need not be exactly PSD, and may be subject to round-off errors, etc. From a theoretical perspective, it helps us evaluate how robust our algorithms are to the underlying assumptions, such as PSD-ness. We provide some initial results on this problem, but obtaining optimal bounds in terms of running time and sample complexity are still open, even when you're allowed to query the whole matrix. Okay, I'll conclude with some open questions and directions for future work. Recently, there has been a flurry of work studying various linear algebra problems for structured input matrices, and this has been fruitful for developing new algorithmic ideas. For instance, special structured families of matrices considered by recent work include distance matrices, Van de Moon and Hankel matrices, and Toeplitz matrices. We can consider any linear algebra problem in the context of structured matrices and design beyond worst case analysis, beyond worst case algorithms for them. Some initial work on this direction appears in a recent paper by Balkan, Lee, Woodruff, and Zhang, where they show how to estimate spectral and Shannon norms in sublinear time. We can also ask the testing version of these questions, where the goal is to figure out whether the input indeed belongs to some structured family of matrices. For instance, we could ask whether the input matrix is PSD or not. We considered this question in a recent work with Nadiia and Raj, which also appears at Fox, and if you're interested, I encourage you to check out the talk. Finally, as alluded to in the previous slide, we can also ask how robust are these algorithms that we mentioned above to the underlying assumptions that we make. And the long-term goal of this is to hopefully develop a theory of robust linear algebra for structured matrices. That's all, and thanks for making it all the way to the end.